Hi everyone, this is Shubha. Uh, Along with Ernest Ryu at UCLA, we are the joint organizer of the seminar series called Friends of Optimization. And today we have a very exciting talk titled Negative Step Sizes Make Gradient-Descent-Ascent Converge. And the speaker is Henry Shugart. Henry is a third-year PhD student in the Wharton Department of Statistics and Data Science at the University of Pennsylvania. He is advised by Professor Jason Altschuler. His research interests lie broadly in optimization and machine learning, with a particular focus on min-max problems. Previously, Henry earned his undergraduate degree from the University of North Carolina at Chapel Hill, where he majored in statistics and analytics as well as mathematics. So Henry, please go ahead with your talk. Really excited about it.
Perfect. Thanks, Shuvo. And before I get started, I just want to thank Shuvo and Ernest one more time for inviting me, and thank everyone on the call for coming to my talk. So today I'm going to tell you all about how negative step sizes make gradient-descent-ascent converge. All of this is joint work with my advisor, Jason. None of it would be here without him. So first, to get started, to start on the type of problem that we're trying to solve today, it's min-max optimization problem. So we have one joint objective function f, which we're trying to minimize in one set of variables x and maximize in another set of variables y. And so this general problem setting has become ubiquitous in machine learning, and optimization, and many fields over the past 100 or more years. So just to run through some applications kind of before we get started that fall into this framework, some of them are adversarial machine learning, where the x minimization variable is the model, so the model weights or parameters in general, and then y is some perturbation that might be trying to fool the model. GANs, generative AI, kind of got its roots in min-max optimization, or at least partially, with x being maybe the generator model and y being the discriminator, so you're kind of competing on some shared objective f. Constrained optimization can, of course, be cast as a min-max problem, with x being the primal variables and y being your Lagrange multipliers. At robust optimization, where x is the decision variables, y is the distribution, and of course, many more problems across math, economics, optimization, you name it. This is kind of a ubiquitous problem setting. And so what does it mean to solve a min-max problem? The goal of min-max problems are in general to find saddle points that satisfy this set of three inequalities that I have written below. And when f of x, or f is convex concave, meaning that it's convex in your x variable and concave in your y variable, which you can kind of think of as a natural analog to convexity in convex optimization or just standard minimization problems. The saddle point condition is going to be equivalent to finding a stationary point. So where the gradient is equal to 0. And this is going to be what we generally talk about in terms of solving a min-max problem throughout this talk. But of course, these two notions are equivalent, so you can think of solving these problems in either way. So now thinking about what the most natural analog to something you would see in standard minimization problems, the most natural algorithm is, of course, or a natural algorithm is, of course, gradient descent ascent, where instead of just taking gradient descent steps in a single variable, you take gradient descent steps in your x variable, and at the same time, you take gradient ascent steps in your y variable, thereby working to minimize x while maximizing y concurrently, or potentially alternating. And so I'm going to point out in the parameterization that we show here, the update x is defined with step size alpha t, and y is defined with the update of y is defined with the step size beta t. They're both parameterized in a way where a positive step size is moving in a natural direction. So for the x variable trying to minimize the objective, a positive step will move in a negative gradient direction, and for the y variable trying to maximize the objective, a positive step size will, of course, go in a positive gradient direction. So one natural question to ask about this algorithm is, does it work? We know that gradient descent works perfectly fine. And so if we just translate it into this min-max setup, do we continue to get the nice guarantees and the, frankly, easy analysis of gradient descent? The answer is surprisingly no. And that standard implementations of GDA can diverge or cycle even on super simple problems. So problems that are convex, concave, and smooth, have all the nice properties that you might think of, and are even potentially as simple as the univariate or bivariate problem min x max y x times y. And so here I show a graph of simultaneous GDA where alpha t and beta t are set equal to each other to some positive value and just constant. And this will actually diverge on the simple problem x times y and alt GDA, where the updates are taken concurrently. Concurrently, where x is updated and then y is updated in sequence. You'll see that the GDA will in fact cycle around a solution and never move closer to the solution of this problem, which of course is at x equals 0, y equals 0. You can check that, make sure that's a stationary point, but I'll tell you now it is. And so based on the ubiquity of this problem and the importance of solving min-max problems, there's been a lot of work on solving min-max problems, including work analyzing GDA. And so I'm going to tell you that GDA can converge in some specific scenarios, specifically when the objective is convex concave and they're uniformly bounded subgradients. GDA can converge only in the average iterate. So the raw iterates may continue to diverge or cycle, even if the average iterate converges in some sense. And so GDA can also converge under strong growth conditions. So if the function f is not only convex in x and concave in y, but strongly convex in x and strongly concave in y, GDA can converge using small enough step sizes, although this is at a provably slow and suboptimal convergence rate on this problem class. And because of these drawbacks, a lot of the work in min-max optimization has focused on on building algorithms beyond gradient descent ascent. So adding extra building blocks, so like extra gradients, optimistic gradients, anchoring are all some classic extra building blocks that have been added on to gradient descent ascent to ensure convergence on more general problems and to avoid some of the problems that occur with GDA. And so today I'm going to be trying to take a step back from those additional algorithms and answer a fundamental question of, can we make GDA converge in its original form? So without any of these building blocks, can we ensure that GDA will actually converge? And so the motivation for this is largely based in some recent as well as classical work about selecting step sizes in convex optimization and how this can lead to improvements in rates. And so dating back all the way to the 50s, it was shown that by modulating the size of your steps, you can get full acceleration on convex quadratics by just changing the step sizes. More recently, starting with Altschuler and Perillo, we've seen that this phenomena extends to more general convex functions and that you can get improvements in rate by just modulating the step sizes. And so, and this is really an active area of research in convex optimization. Here, we're not worried so much about getting improved rates, but rather trying to change from divergent or cycling behavior into convergent behavior. So can we even change GDA from diverging to converging at any sort of rate to begin with? And the answer to this question we show is a resounding yes. We can make GDA converge only changing the step sizes alpha t and beta t. And how we do that is by using negative step sizes. This means going backwards at various steps so that either the x or the y variable will make, in some sense, backwards progress, at least on some iterations. And that surprisingly, this backwards progress is important in forcing GDA to converge and really seeing this convergence. And now I'm going to move on to show a simple example and go walk through a simple example of how we derive these negative step sizes and why they might work. And so we're going to focus on this bilinear problem, min x, max y, x transpose by for some matrix B. We can think of this as a multivariate generalization of the kind of bad case that I showed in the previous couple of slides of xy. In fact, this is exactly the case when b equals 1 and x and y are both univariate. And so for the sake of analysis, we're just going to consider that the singular values of b are lower bounded and upper bounded. The technical assumption is on the slide if you want to see that. And one really nice thing about GDA in this setup is that the gradient of this function is completely defined by a linear function. It's a matrix times a vector. And therefore, we can write the update as a discrete time linear dynamical system. And so here we can see that the tth iterate of x and y is defined by the product of these matrices UT, so the update matrix on the tth step, times the initial iterate x0, y0. And so this makes our life easy in that we can analyze the spectral properties of UT to get some insight about what step sizes we might want to take. So before we look at what step sizes we might want to take, we should look at what step sizes we can't take, else we're going to diverge. And so surprisingly, it's easy to show that GDA fails with 3 different categories or 3 different families of step size schedules that are all perhaps logical, and maybe the first initial choices for step sizes. So GDA will fail to converge even on the simple problem min x, max y, xy for any of the following step size schedules. So constant step sizes where alpha and beta are taken to be constant over iterations. Symmetric step sizes where alpha and beta are equal to each other on every step. Or for perhaps the most surprisingly, if alpha t and beta t are taken to be non-negative on every iteration. So if we're always moving in what seems to be the correct direction of the gradient, we're going to provably diverge, even on a simple problem like min x, max y. And now I'm going to show you some simple proofs, but the important thing to take away from this slide is that standard step size schedules will fail. And the proofs are just simple, and so I'll show them to you because they're simple and illustrative. So first, constant step sizes.
Henry.
Yes.
So one quick question. Yeah.
Yes.
So in the literature, what are the most? So all these 1, 2, 3. These are the most common step sizes, right? Like
yeah. So every standard step size schedule will fall into at least one of these. So simultaneous gradient descent, which is maybe what some people would call like the gradient method, or like historically have called the gradient method, it's going to be constant, symmetric, and non-negative. So it's going to be alpha t equals beta t on every iteration. It's just the same. This is the naive thing to do. Alternating GDA is always going to have non-negative step sizes, although they are going to be time varying and asymmetric, because on each iteration, one of the 2 step sizes is going to be 0. And then something like 2 time scale gradient descent ascent is probably going to be constant and non-negative.
Okay, good. And everyone else, like, please interrupt Henry, like anytime you have a question. Okay, so
yes, please interrupt me whenever throughout the talk. I'm happy to field any questions. Okay, so to show that constant step sizes don't work, all we have to do is look at the eigenvalues of the update matrices UT. They're all the same, and so it's the same as looking at just the update matrix U0. The eigenvalues are in fact 1 plus or minus I times square root of alpha beta. Of course, one of these, no matter what alpha and beta are, one of these 2 eigenvalues is going to have a magnitude greater than 1. And therefore, the spectral radius of the larger update matrix is going to be greater than 1, and so you can't converge. Now, for symmetric step sizes, of course, the product of the determinant of the final update matrix is going to be the product of the determinant of all the update matrices. This is the product of something that turns out to be 1 plus a square number. meaning that the final determinant is certainly greater than 1. And therefore, similarly, the spectral radius must also be greater than 1. By analogous argument, non-negative step sizes also don't work. It's going to be the product of alpha t and beta t on each iteration. The product of two non-negative numbers is non-negative. And so now I've just shown you that no step size schedule that falls into any of these three categories is going to work. And so we need to break all three to find a step size schedule that does work. So we're going to need a time varying, asymmetric, and occasionally negative step size schedule. Of course, I just showed you that these three kind of things prohibit convergence, but I haven't shown you that breaking these three characteristics will enable convergence, but I'll hope to convince you of that by analyzing this, a simple case where we have all three characteristics. And this is going to be what we call the slingshot step size schedule for problems with linear gradients. And the slingshot step size schedule that we define here is that alpha and beta alternate taking positive and negative steps. And so on each iteration, in each pair of iterations, alpha is first going to take the x player is going to take a positive step. So it's going to take a gradient descent step, while the y player takes a negative step, similarly doing a gradient descent step. And then they're going to both switch on the 2t plus 1 iteration. So the next iteration, now the x player is going to take a positive gradient step in conjunction with the y player. And it's going to be of equal magnitude, only one parameter every two steps here. And so just to make sure that it's time varying, yep, alpha t, it won't equal, alpha 2t does not equal alpha 2t plus 1, similarly with beta. It's asymmetric. Alpha t is taking a positive step. Beta 2t is going to be negative. And then it's also going to be occasionally negative. Half of the steps are going to be negative. And so now I'm going to move on to the analysis of this slingshot step size schedule for our bilinear problem. And we're going to focus on just analyzing two steps to start with. So between x0, y0, and x2, y2. And all we have to do is write out the two updates and look at them together. And we can see that some simple matrix multiplication gives us that the joint update matrix, u1 times u0, is going to be the identity minus some value h squared times a positive semi-definite matrix. Of course, this leads to a two-step contraction, but what's potentially most interesting here is that on each of the first two steps, the value, the distance to optimum may actually increase. So that on each of the first two steps, an expansion is possible. X0, Y0 might move farther away on the first step, or it might move farther away on the second step. But between the two steps, we're guaranteed to decrease the distance to the optimal solution. And before we move on, I'm going to point out one thing. That is the contractive term, this h squared that we get on the diagonal is alpha 0 times beta 1. This is going to come up later, but it's important to note that this product between kind of the cross terms in our step size schedule is the term that we want to be beneficial. So it's going to equal h squared here. In general, we're going to want it to be positive. Okay, so why are these positive negative step sizes good? I just showed you some analysis that might look a little bit like an algebra trick and so I don't really blame you if you're not convinced yet, but hopefully I can show you that this is more than just an algebra trick and that it's doing something that at least on the surface makes a little bit of sense. So using the slingshot step size schedules, we're going to see that the update in some joint variable z is going to first be a gradient descent step on the entire function f, and then a gradient ascent step. So it's a gradient descent step followed by a gradient ascent step. And so why is this a good idea? The key idea here is that the descent step followed by the ascent step cancel to first order. So the gradient direction kind of vanishes, and it leads to some movement in a new second order direction. And so we can think of this kind of similarly to parallel parking, where you start kind of next to the spot you want to be in. You drive forward a little bit and you drive backwards a little bit after turning the wheel. And the only thing that you're going to get any noise, any signal from is that wheel turn. And so you move a little bit to the side. And so this is maybe the heuristic behind our step sizes, and this forward backwards movement canceling to lead you just a little bit in a sideways direction. And so now to make this a little bit more precise, we can do a Taylor expansion around Z0 and look at what the difference between the gradient at Z1 and the gradient at Z0 looks like. It ends up being exactly h times the Hessian of f times the gradient of f. On face, this might not be a particularly interpretable quantity, but in fact, this is the gradient of the Hamiltonian function. So the gradient norm squared 1/2 times it, but the Hessian vector product that we're seeing, or the Hessian gradient product that we were seeing in the previous slide, is in fact the gradient of phi. And why might this be a good direction to move in? Because we're looking for a stationary point. And so by moving in a negative gradient direction of phi, we move towards stationarity of the entire function f. And so that 2 steps of slingshot GDA are approximately equivalent to 1 step of Hamiltonian gradient descent. And it's important to note that the Hamiltonian is a shared objective, that x and y are now collaborating to find a stationary point, instead of competing to find a min-max point. So now instead of looking for a saddle point, we're looking for a minimizer of phi. And so it's at least a little bit of a sensible direction. Now I'm going to show you what this looks like in the specific example of the bilinear game, or the bilinear objective. So the Hamiltonian for bilinear functions is little m strongly convex quadratic and m smooth quadratic. And these values come from the spectral bounds that I showed you a couple slides ago. This is a nice function to optimize, in that we know that how to optimize a strongly convex and smooth quadratic. There's a lot of good methods for that. And another good thing about the bilinear example is that in the bilinear problem, the Taylor approximations we made are exact. And so that what I showed you on the previous slide, that 2 steps of slingshot GDA are approximately 1 step of HGD. In fact, 2 steps of slingshot GDA are exactly 1 step of HGD. And so now we have that the 2-step update is 1 step of gradient descent on a m strongly convex quadratic, little m strongly convex quadratic, and m smooth quadratic. And we know that we can accelerate in this problem class. And so we can accelerate using standard techniques from the paper by Young in 1953 that I told you about, or that I mentioned as motivation for this entire project. And how we do this is that we take HT to be the square root of the step sizes for the strongly convex and smooth quadratic. And we exactly recover the Chebyshev step sizes of Young, and therefore we exactly recover the rate that he showed in 1953. And here I show in the plot a plot of what the step sizes look like for 16 iterations of GDA with the slingshot step sizes with time varying step sizes to get the Chebyshev acceleration. And as you can see, both players alternate. The magnitudes change a little bit across each iteration, or a lot. In fact, there's quite a large gap between the smallest step and the largest step. And so the acceleration that we get recovers a convergence rate of square root of the condition number of the problem times log 1 over epsilon. Perhaps more interesting, we recover the exactly optimal rate among all first order methods on the bilinear problem using only gradient descent ascent. And so what's interesting to note here is that without using any of the extra tricks like extra gradients or optimism, we can recover the exactly optimal rate, and therefore kind of trivially, we can recover the exactly optimal rate using any of these tricks as well. And so now I'm going to, I just told you about how we can, the bilinear example. And so I'm going to show that this is not just locally, that the results I've shown you aren't just local to the bilinear problem, but are in fact expand a little bit more, and in fact a lot more, by showing you that it works on the quadratic objectives. So if we add a regularization term to the x and the y variables, so now we have a quadratics, or a quadratic penalty in x and a quadratic penalty in y, we're going to see the same types of results hold. And so this problem is, of course, equivalent to just a larger quadratic, the product kind of z transpose hz, and that this is a strictly more general class than the bilinear objectives, because when you set a and c equal to 0, you recover the work that I just showed you. And so the two-step update of Slingshot GDA it can be written by a simple product of I plus little h times big H times I minus little h times big H. And this, you might observe, is the difference of squares. And so it's going to be the identity minus little h squared times big H squared. And then based on the definition of h is symmetric. And so we know that h squared is going to be positive semi-definite. And if we take little h to be small enough, we're going to have a contraction, or at least we're going to move closer to the solution point. And you can also note that, again, we recover exactly one step of Hamiltonian gradient descent with 2 steps of Slingshot GDA. And so that by carefully choosing HT and modulating the size of our steps, we can get an exactly optimal convergence rate as well. This is, unlike the bilinear problem, an exactly optimal convergence rate on this class of problems was previously unknown. And so that it's interesting to note that GDA is the first algorithm to achieve this, even when other more sophisticated algorithms could not. And so now I'm going to move on to more general objectives. But before I do that, I'm going to pause and wait to see if anyone has any questions about the linear case. Okay, hearing none, seeing none, I'm going to move on and tell you about problems with linear gradients. So, or beyond problems with linear gradients, sorry. So the positive negative step sizes that I just talked to you about kind of have a natural flaw, in that if the gradient at the update at x1 is the same as the gradient at x0, of course, they're going to cancel exactly, and we're going to have a kind of trivial cycle. And this is the case in even the simple problem of the Huber function. So taking anywhere where the function is locally linear, taking a positive and negative gradient step is kind of nonsensical. And so the takeaway here is that we're going to need to change the Slingshot step size schedule from what I just told you of these positive negative gradient steps, and move to something that takes more forward steps than backward steps, so that in this minimization example, we're actually moving in a negative gradient direction, and we can ensure progress even when even when the function is locally linear. And so,
sorry, Henry, I have a question.
Yes.
It took me some time to. Could you go back one slide?
Yes.
So, yeah. So here, you're constructing your method so that each 2 steps becomes I minus order h squared. And
Yes.
as you're saying, the first order terms cancel out. That's sort of central to your analysis intuition.
Absolutely.
The other methods that are convergent, right? So like the extra gradient method, the optimism method, these, can you remind me, do these have a surviving first order term, or do these also like cancel out the first order term?
Yeah, so they all do have surviving first order terms, and their first order terms are all going to be effectively the standard gradient descent ascent update. So it's going to be like a negative gradient step in X and a positive gradient step in Y. That's going to be the surviving term. And then the benefit or kind of the correction term so that it doesn't diverge is going to be some second order term that is helpful.
So the extra gradient method, if I remember correctly, and correct me if I'm wrong, is also up to constant optimal for the for the class of bilinear problems, right?
So the class of bilinear problems, it is not, in fact, optimal. I think that you need to, using the assumptions that we had, the little m and big M spectral bounds, you need to do something additional to get the optimal rate. So we get a square root of this condition number. I think that they only get, I think extra gradient only gets the condition number exactly.
I see. So in a certain sense, then the fact that they have this surviving first order term is kind of, at least for these bilinear problems, is an indication that maybe their method, the existing method, is wrong, maybe.
Potentially, it's potential. I guess I can't rule out the existence of some method that has some first order surviving term, but yeah, I think that in the bilinear problem, the first order term is not in general helpful. In that XY example, it's spiraling out, and so by removing this, you're going to have a better algorithm, or at least an algorithm that might converge faster in theory.
Okay, thank you.
Yep. Okay, so going back to this family of step sizes that we propose in our work, we propose a family called the slingshot step size schedules, which satisfy a set of 3 conditions every 2 iterations. So the first condition is that at least one step size is negative. So one of the 4 steps across 2 iterations is strictly negative, not just 0. And then we're going to have this alternating products condition where alpha 2t times beta 2t plus 1 and alpha 2t plus 1 times beta 2t are greater than 0. And so if you recall, in the bilinear example, these are the terms that I called out as the benefit term. So they're the diagonal terms. This is the h squared in the bilinear example. And so this is really what drives the contraction, at least in that example. And then consecutive sums are going to need to be greater than or equal to 0. So alpha 2t and alpha 2t plus 1, and similarly with beta, just to ensure that are going to need to be greater than or equal to 0, just to ensure that we're making more forward progress than backwards progress to deal with the kind of Huber function case that I just showed you. And so what we propose, this definition is going to lead to some step size, to the sign patterns that mirror the sign patterns I showed you previously for the linear slingshot step size schedule, where either the X player or the Y player is taking a backward step on each iteration, and then they flip-flop on the next iteration. And so we're going to focus on one family of, or one specific instance of the slingshot step size schedule. And it's going to be what we call the slingshot step size schedule for problems with nonlinear gradients. And so for every iteration, we're going to flip a coin, and we're going to take the same first step as in the linear case. We're going to take a positive gradient step in the X, or a negative gradient step in the X variable and a negative gradient step in the Y variable. So the Y variable is moving backwards, or vice versa. And then on the second iteration, we're going to take, for whichever player just took a backward step, we're going to take a forward step. And then the other player is just going to do nothing. They're going to not move at all on the second step. And so here, we kind of get some symmetry back by flipping a coin every iteration. And I want to point out that this is not the only step size schedule that will work for convergence on nonlinear problems. It's just one instance that we chose to analyze because it's nicely parameterized by one parameter, and it was easier to analyze than some of the other step size schedules. I'm also going to just make one quick remark that we don't analyze this step size schedule for H varying in T. We're only going to focus on H being fixed throughout the optimization, at least in this part. So to look at how this, how we just changed the step size schedule and how this is going to change the second order expansion. So what this affects in our HGD interpretation, we're going to look at one of the two instances, either, we flipped heads or we flipped tails, and see that the Taylor expansion or the Taylor approximation of the gradient at Z1 is going to be the same as before. And so now, by just taking a step in one of the two variables, on the second step, we have that variable, so in this case, the y variable, takes HGD step, at least in the portion of the HGD step that the y variable would be taking originally. And then the x player is just going to have quit after the first step. And so it's going to just take a first order gradient descent step. And so now, and so averaging across the two coin flips, we see that the expected update direction is going to have two terms, not just the HGD term, but also an additional GDA term. So a standard GDA step, symmetric, equal magnitude step, as well as this HGD term. And so for some of you in the audience who might have done more work with empirical machine learning, or especially on GANs, you may have seen this algorithm before. This is a previously proposed algorithm called consensus optimization, and it was shown to be extremely effective in optimizing GANs, where GDA and HGD are both kind of lackluster in terms of empirical results. And so here it's interesting to see that the slingshot step size schedule recovers approximately this consensus optimization update. One thing that I'll note is that our main results on our convergence don't rely on any proofs of convergence for consensus optimization. There are some, but they generally require more smoothness assumptions or just settings that are perhaps less standard than the convex concave setting. We believe, however, that perhaps the slingshot step size schedule in this comparison could be useful in proving convergence analysis for consensus optimization. So going the other way and analyzing a second order algorithm as an approximation of a first order algorithm. So moving on to the convergence analysis that we do, we use we analyze convergence by analyzing a Lyapunov function that decreases every two steps. Similar to the example that I gave with the bilinear problems, we know we're not going to be able to show convergence by doing anything over just one step. We're going to need to look at least two steps. And so that's what we do here. We show progress in a quite simple Lyapunov function of the distance to optimality. And that on every two steps, we're going to see a decrease in that value, or at least, non-strictly, by a factor of that's proportional to the gradient norm squared of that value. The proof of this, I'm not going to get into too much. It's based on sum of squares and performance estimation problems. I'm sure there are many of you in the audience who have done great work. I know Shuvo and Ernest both have on this area. It's a little bit technical, but the main idea is that we're setting up a performance estimation problem for the convex concave problem class and analyzing it there, and using that to analyze our step sizes. And so what does this two-step lemma imply for convex concave functions? It implies that we get convergence. And so that's really the main result for convex concave functions, is that don't worry about the rate. We have convergence for the first time of GDA using only step sizes. And in fact, we do get a 1/t rate in the gradient norm squared. And the proof of this follows from just telescoping that two-step lemma that I showed you t times. And so the 1/t rate nicely matches classic algorithms such as extra gradient and optimistic gradient. It's not optimal, so there has been more work recently that's gotten an accelerated rate of 1/t squared. Ernest was kind of the originator of that work, and there's been a lot more algorithms that have gotten this 1/t squared rate since. It's an open question of if GDA can get a rate either better than 1/t or all the way up to that 1/t squared boundary. So, you know, if it can get 1/t squared or 1/t plus 1/t to the 1 plus epsilon, either of those would be very interesting by just changing step sizes. And so here I show the convergence of the slingshot GDA that we proposed in comparison to extra gradient and optimistic gradient on a simple problem. We can see that although slingshot GDA does slightly worse than extra gradient and optimistic gradient, it matches in the slope of this line, which is on the x-axis iteration and the y-axis the gradient norm squared, which means that it's getting the same rate. It of course doesn't match the extra anchored gradient. That's the 1/t squared. That's the 1/t squared rate. And then in the second plot, I show the fit of a 1/t algorithm. So just like if some constant times 1/t fit to the algorithm, it matches almost exactly. You can barely see the dashed black line over the blue line. And then I show the box and whisker plots quantify how much that coin flip kind of moves, disrupts the convergence. And it seems to be quite consistent in that even in the, tail quantiles, there's convergence at close to this 1/t rate. And so moving on from convex concave, which we show for the first time the GDA can converge, I'm going to show some results for strongly convex, strongly concave problems where it's been known that GDA can converge either at a couple of suboptimal rates. So here we show convergence in the distance to optimality at an order of kappa log 1/epsilon rate. This is in fact at least rate optimal. It's not exactly optimal. We don't make any claim of that. And what's interesting here is that this improves over the rate of simultaneous GDA, which gets a kappa squared times log 1/epsilon rate, and alternating GDA, which gets a kappa to the 1.5 log 1/epsilon rate. And so that slingshot GDA improves over all other known instances of GDA, at least in the strongly convex, strongly concave setting. And so now to summarize some of the results about convergence that I've just showed you, for problems with linear gradients in both the bilinear and quadratic settings, we get exactly optimal convergence rates. And in the quadratic setting, this is for the first time. In problems with nonlinear gradients, so in convex concave problems, we get convergence for the first time, and we get it at a standard rate, nothing flashy, but also not terrible. And then in the strongly convex, strongly concave setting, we improve the convergence results for GDA, improving to the optimal rate. And so, yeah, so kind of the biggest takeaway here is that by taking GDA, by taking GDA in its original form with a kind of perhaps puzzling step size schedules, we can enable convergence. And so the convergence really relies, it's both necessary and in some ways sufficient, that time varying asymmetric and occasionally negative steps can guarantee convergence. And that these three properties are key in the intuition behind the slingshot step size schedule. So some open directions that this work leads to, and some open kind of natural questions to ask are, if some of these same ideas can be applied to other algorithms. So can other algorithms benefit from time varying asymmetric or occasionally negative step sizes? Could we combine these with something like extra gradient or optimistic gradient and see improvements in the rates, or lead other algorithms to converge for the first time? Also, another open direction is other settings. So of course, I just showed you for convex concave problems, and that does give a nice overview or a nice first step. But of course, constrained optimization problems, even constrained convex concave problems, are natural for things like constrained optimization. And so it would be nice to get convergence results in these settings with slingshot step sizes or GDA more generally. In stochastic or non-convex setting, non-convex, non-concave settings, these might be necessary to prove convergence or to improve convergence for GANs empirically. And so that analyzing slingshot step size schedules in these settings might also be interesting. And so now I'm going to, that's the end of the talk. And thanks again, Ernest and Shuvo, for having me. And anyone who has any questions, feel free to ask. I think we have some time.
Yeah, so fantastic talk, Henry. And I think this is one of the fewer cases, like where the speaker actually finishes. Usually what happens, people take longer, right? So this was great. One question that I have, right? So
Yep.
Can you go back to the slides where you were showing the convergence rate of different algorithms?
Here?
Yeah. Okay,
Yes.
so here when we're showing alternating gradient descent ascent, right? So essentially the algorithm is that the second iterate is using the latest information from the first iterate, right? So that's alternating gradient descent.
Yes.
Okay.
Yes.
And what was the step size that you were using for this?
For alt GDA?
Yeah. So this is the one that is cycling, right?
Yeah, I don't remember exactly what the step size is. It's largely invariant. I took it small enough so that it would cycle. If you take it too large, it will diverge and not even cycle. On this problem, it wasn't a matter of shrinking the step size. Shrinking the step size would only kind of narrow this yellow line so that there's less oscillation.
Okay. And another question that I had is, in your proofs, the performance measure is distance from the solution point?
Yes.
Like all through, right?
Yes, exactly. That's
okay.
Well, so the performance metric for convex concave functions is in fact the gradient norm squared. We show like a Lyapunov function on the distance to optimum, but because it's kind of nonsensical to show convergence in distance, kind of for similar reasons in convex optimization, why if you have just a convex function, you can't show convergence in distance. You have to show convergence in gradient or function value.
Yeah.
So
did you try any other performance measure? Like some people, they use like duality gap, right?
So duality gap it is a little bit I guess tricky, because there's a lot of different ways that you can define the duality gap in the most rigorous sense, where it's the max of with respect to y and the entire set. It can be potentially unbounded. So like even in the bilinear problem, it's unbounded in general. And so there's some subtleties there. Certainly there are a couple of other performance metrics that we can show convergence in. the gradient norm squared felt like the most natural. It's also substantially, it makes for a nicer comparison to some of the other ones. So.
Okay, so that was my question. If anyone has any questions, please feel free to ask.
Yeah, so I have a question. So have you, so perhaps the obvious sort of next thing one could try is we're doing this in a constrained version, right? So some sort of projected version of this thing. Is this something that you've tried? Is there any technical sort of difficulties that prevent you from prevent the analysis from going through?
Yeah, so I think with constant step sizes in the projected setup, you can kind of get to trivial examples where you have an alternate, like a bad cycling behavior where the projection, if you project in the middle of the two steps, it can throw things off in a way that's not very nice. And you can observe this empirically, like just implementing the slingshot step size schedules naively with projections doesn't yield very good results. I mean, you can implement it even like on a linear program or something where you add some constraints, and there are definitely some problems that show up that are non-trivial. And so that's something that I've been thinking about for sure, of how we can add in projections or potentially other methods of adding constraints, like doing mirror descent or something.
I see. But you could do the projection after the two steps, right?
Sure, yes. And that also, there seems to be some strange behavior empirically. I don't have a great a counterexample for you, but definitely I didn't, it doesn't seem to always work as nicely as
I see. Okay.
So
I see. Yeah, so another question. So, I mean, this this algorithmic component where you take negatives, like the idea, just the keyword of negative step size is just like weird, right? It's very unusual. Do you know, like, have your advisor, for example, thought about using negative steps in just the convex minimization setting, like, you know, his work on the silver step sizes, that kind of stuff? Was that a search over all positive and negative steps, or like, do you know if there's any benefit in doing negative steps in that setting?
So that's a good question. I think that we've kind of we haven't done anything truly, exhaustive or really done a deep search into this, but there are some heuristic reasons why you might not want to do negative steps. So doing like Hamiltonian gradient descent for, let's say, convex quadratics won't get you optimal rates. The Hamiltonian somehow makes the problem, like doing gradient descent on that problem makes the problem harder instead of easier. And so at least there are a couple of heuristics that will tell us that it might not be the reasons that you might do negative step sizes in min-max optimization don't really carry through to minimization. Although I do think that that's an interesting question that's, at least I haven't fully closed about if there's some benefit in minimization of doing step sizes.
Yeah, so another thing that just crossed my mind is, so in deep learning, there's this thing called sharpness-aware minimization. And it kind of resembles the extra gradient method, but the sign is a little bit flipped. So basically what you do is at your current point, you do a gradient ascent step. It's not min-max optimization, it's just like min training, but you do a gradient ascent step, take the gradient from there, and then return, and then take the gradient step from the ascended point. And the reason people do sharpness-aware minimization is because not because the training loss goes down quicker or anything, but because it somehow improves the generalization performance. And initially, when this came out, it got a lot of attention because it had a small but pretty consistent improvement in terms of the deep learning performance metrics. And also, but some people pointed out that, oh, this is sort of similar to extra gradient, but I don't think people really have explore that direction very much. So I guess I would say that that's the only instance before your paper where like something like a negative step size. I've seen that before, but do you feel that there's any connection with your line of work with that?
Yeah, I guess I haven't investigated sharpness aware minimization too deeply. I have seen there's some other work in non-convex minimization problems where negative step sizes are taken for like line search, and it seems generally that this has something to do with dealing with problems around non-convexity, and that a negative direction is potentially helpful there. I think that there's some key differences between the convex concave setting and the non-convex minimization setting. Just that you don't have these same type of examples where the negative direction is helpful in as clear of a way. But yeah, I guess I should look into the sharpness aware minimization a little bit more.
Great. Yeah, thanks.
Sounds good. So thanks everyone. So I will stop the recording now.